Functions of several variables. In the last very basic recording, we have seen the maximization of function of one variable. Let us now first of all see functions of several variables. So in economics, we hardly get any instance in which we are interested only in the function of one variable. So generally, supposedly if I'm the consumer, I'm not consuming just one good. I'm consuming several goods at the same time. So that is function of several variables. Supposedly you are a producer. You're not just going to use one input to produce anything. You will be using several inputs to produce. So that production function become the function of several variables. So we are hardly interested in the function of just one variable. So we are more interested in the function of several variables, right? And we are also interested in the trade-offs among these variables so that we are able to maximize the production. So as we are able to minimize cost, so as we are able to maximize utility, right? So we're going to look at the functions like this. We are more interested in the functions like this, where y is the function of several variables. One thing. So we are interested in the point where y is reaching the maximum and the trade-offs which are going to happen between the several variables so that y reaches its maximum. We are interested in that. So because in order for y to reach its maximum, sometimes I think we might have to use more of x1 or less of x2, more of x3, less of x2, so on. So what we are interested in is where y is reaching maximum and what are the trade-offs between these several variables so that y reaches its maximum. That's an idea. So for example, the functions like this, qd equals to or also write that demand is the function of prices and income. So it is the function of several variables. For example, 10 minus 2p plus 0.2i, or you have the utility function uxy. For example, x to the power 1 by 3, y to the power 2 by 3, something like this. Or you are interested in the production function. That is also the function of several variables. Say, for example, 10 into k to the power 0.4, L to the power 0.6. So I'm just giving an example. So all of these are the functions of several variables. And one more thing that I want to tell you. So in this very basic series, I am just doing that much of maths which is required for the micro course. So don't think that this is the complete series of mathematical economics. So for that, you have to see what Vidhi is doing. So she's also starting from very basic and then moving up. So look at those videos which Vidhi has uploaded for the mathematical economics. So I am just doing those topics which are very useful for me while solving the optimization problems in micro. That is what I'm interested in. Okay, so if the function is of the several variables, we are interested in the partial differentiation concept. So we are trying to measure the effect of change in x1 on the dependent variable y, keeping all other variables constant. So for example, y is the function of x1 and x2. So if either of x1 and x2 is going to change, y is going to change? Yes. So in partial differentiation, what we do is that we try to find out the change. We try to measure the change in x1, which is going to be affecting y, keeping x2 constant, or how the change in x2 is going to affect y, keeping x1 constant. That is what we are interested in, right? So we are looking at the partial differentiation of the function instead of the differentiation. So in differentiation, you have just dy by dx. Here you have del y by del x. That is what we are interested in. So if the function is like this, fxy, so when I say del f by del x, so I'm not using df by dx, I'm saying del f by del x. So the moment I use del, it means I'm not using beta df by dx. No, I'm using del f by del x. This is what I'm using. So I'm not using this, but I'm using this. Means when the moment I use del instead of d, it means that I am only measuring the change in f due to the change in x, keeping all of the variables constant, right? Or the another way it is represented is f subscript x, like this. So this is nothing but the rate of change in fxy by varying x only, keeping y constant, right? So rate of change in fxy when only x changes and y remains constant, right? Similarly, when I say del f by del y, or I say f subscript y, so fy. So it is the rate of change in fxy due to the change in y, keeping x constant. That is what. So these are called the partial derivatives. So partial derivative is different from derivative because in partial differentiation, we are measuring the change in the dependent variable to the change in only one independent variable, keeping all others constant, right? That's what you do. So for example, you have the function like this. Right? So if I want to find out del f by del x, so I won't be writing it this way every time, but just for the first time I'm doing it, so it is like this. Right? But this is 0. That's just a constant. 2x's derivative with respect to x is 2. And 4y's derivative with respect to x is 0 because y is a constant. So this comes out to be 2. Right? Or del f by del y, del 10 by del y, plus del 2x by del y, plus del 4y by del y. So that would mean 0. Del, now you are differentiating 2x with respect to y. Now 2 is a constant, x is also a constant because you're differentiating it with respect to y. Only y is the variable. So that is 0. And 4y's derivative with respect to y is 4. So this guy is 4. So one thing you should understand is that all rules of differentiation will apply to also partial differentiation. All rules of differentiation. The only thing is that at a given point of time, you're changing only one variable, keeping all of this constant. That is the only thing. So I will write this line. All rules of ordinary differentiation apply except that at a time we change only one independent variable and keep all other independent variables constant. And keeping all other independent variables constant. For example, you have fxy equals to 10 plus 2x square plus y cube. So if I want to find out del f by del x, so 10 is just a constant. 2x square's derivative with respect to x is 4x. And y cube's derivative with respect to x is 0. So that is 4x. Del f by del y, 10's derivative with respect to y is 0. 2x square's derivative with respect to y is 0 because x is a constant now. And y cube's derivative with respect to y is 3y squared. Right? Then you might have a function like this. fxy equals to 2x squared 6x plus 4y. Right? Again, the rules of partial derivative, rules of product rule is going to apply. So when you do del f by del x, first function as it is, into derivative of the second function with respect to x, that is 6, plus second function as it is, into derivative of first function with respect to x is your 4x. Right? So I hope you guys can just solve this yourself. Then del f by del y would be first function as it is into derivative of the second function with respect to y is 4, right? So it is and second function as it is into derivative of the first function with respect to y is 0. You guys can calculate this. This is going to come out to be 8x squared. This is going to come. Guys, you with me? Right. So the point is that all the ordinary rules of differentiation will apply here as well. Then you have the second order partial derivatives. Second order partial derivatives. So when you have found out the this guy, for example, just have a look at this del f by del x in this case. So del f by del x itself is a function of two variables. So you can say that the partial derivative of the function is also the function of the n variables. So that is again, so here now we are trying to find out the derivative of a derivative or a partial derivative of the partial derivative. So when you are taking the partial derivatives of the partial derivatives, that is the higher order derivatives, right? And these higher order derivatives are very important for us to check whether second order conditions are holding, to check concavity of the function, for those things. So these are important. To check concavity of a function. To check second order conditions, whether they are holding or not. So I'll be telling you about that. So assuming that fxy is a continuously differentiable function in the open region. So you can find out the second order derivatives. It is C2. Okay, let me not get very technical out here. it is a continuously differentiable function. So you can find out the first order derivative, you can find out the second order derivative, and so on. So you can derive these. So you have, there are two kinds of things. One is the direct second order partial derivatives. Direct second order partial derivative. So for example, you have the function like this, fxy as x square plus 5xy plus 2y square. So del f by del x is 2x plus 5y, and del f by del y is 5x plus 4y, right? So the direct second order derivative is what? Fxx, or del 2 f by del x2. Okay, or you can also write del fx by del x, or you can also write fxx. So that is 2, or del fy by del y. That is, you here it is the partial derivative of y. You are finding the partial derivative of y. You are finding out the partial derivative of y with respect to y only. That is how this partial derivative of y itself is changing as y is changing. That is what you're finding out. So that is 4. So these are the direct partial, direct second order partial derivative. So fxx and fyy. And then you have cross partial derivative. Cross partial derivatives. So cross partial derivatives are what? You are finding out how the partial derivative of x is changing as y is changing, or how the partial derivative of y is changing as x is changing. So it is what? How the partial derivative of x is changing as y is changing, fxy. That is del fx by del y. So you differentiate the partial derivative of f with respect to y, and this comes out to be 5. Or how the partial derivative of y is changing as x is changing. That is del fy by del x. That is how the partial derivative of y is changing, 5x plus 4y, as x is changing. That is 5. So you can just write this thing as, don't have to write fx in parentheses and y, just write fxy. So we understand this. And this is as y, fyx. So you can see that the cross partial derivatives, they are equal. So Young's, this is called the Young's theorem. So just remember the thing about the Young's theorem, that under quite general conditions, what is true is that the order in which the partial derivative is conducted to evaluate the second order partial derivatives, that is immaterial. That doesn't matter. So whether you find out how fx is changing as y is changing, or you find out how fy is changing as x is changing, that doesn't matter. The cross partial derivatives are equal. This thing, just keep this thing in hand. That is what Young's theorem is telling you. So I'm not getting into detail about this right now. Just this is enough for us. That is for Young's theorem says fxy equals to fyx. That is the cross partial derivatives. They are right. So this is about your one of the very basic recording in which we've talked about the functions of several variables. I'm again reiterating one point. I am doing these videos only for my micro course. I'm only doing that much of maths which is required for my micro course. For the detailed maths videos, I think you should look at the basic series of which is uploaded by Vidhi. Right? Chaliye. Thank you, beta.